So for those of you who want to watch this through YouTube, it should be up already. Alrighty. Alright, so just send a text message to the class that the live stream should be up now. So this way people who have been waiting for the live stream link to be on can now participate on the other side. Alright, excellent. Thank you. Thank you for the confirmation. And so today is going to be the first day that we are transitioning to actually programming. Well, I know, the positive and negative exponent is kind of programming, but now we are talking about actual assembly language programming. Well, sort of. Okay, so what we'll do today is we're going to take a look at the tool chain. So your lab is going to be this part here. It's going to be familiarization or familiarizing with the TTP tool chain. Some of you may remember TTP refers to Tax Toy Processor. And I'll be spending some time today to talk about the architecture itself, some time to talk about the tool chain, so that by the time we get to the lab time, you guys will have everything that you need in order to use the tool chain. So it's going to be a little bit exciting, and it's going to be quite dense in terms of information content. So I would highly suggest everybody to take notes today. And I know sometimes I talk maybe a little bit fast. So what you can do is to jot down the timestamp and what I talk at a particular time. So when I transition and start to talk about something that seems to be important, you just kind of take a note. Okay, you just take a note. This is the time, and this is the topic that Tech is starting to talk about. So by the time we get to the end of the lecture and you need to do the lab, you can then refer back to a specific timestamp, to kind of retrieve what I talked about a specific topic. That's a good question, Omer. Let me think. There are probably a few reasons. One is I don't want to use the Intel processor. That's for sure. And the reason why I don't want to use the Intel processor was it was twofold. Okay, the first one was it was a dirty processor. What makes my processor different? Can I answer that question with a self-referencing answer? My processor is different. It doesn't use the Intel instruction set for one thing, and the internal structure is very simple also. So everything you can actually see it. But going back to Omer's question, one of the main reasons is I want to show you guys what the components are inside the processor and how they interact with each other. And the reason why I want to show that is because before this approach, okay, before I actually talk about what is inside the processor, I just teach assembly language programming like everybody else in the district. But then I ran into a problem. People, associate the syntax of the language with what they want the processor to do, which doesn't work, okay? Because the processor is hard coded, or it is, by the hardware design, it can only do certain things. It's not because of the syntax, that the processor is able to do something. The syntax is really just saying, okay, of all the things that you can do, processor, I want you to do this at this particular memory location. So I found that most people do not understand what is actually going on, unless I explain what is inside the processor first. So all the pathways, inside the processor, which are implemented using the things that you guys have been kind of playing with, the multiplexer and the demultiplexer, the registers, memory and stuff, and wires and splitters and RAM and ROM and stuff like that. So with an understanding of what is inside the processor, it becomes, I'm hoping, it becomes more intuitive of why certain things can be done and why certain things cannot be done. More emphasis to what cannot be done because of the limitation of the processor. So that was the main motivation of why I have my own processor. And then a side effect, which I never thought about, but until somebody told me about it, is, oh, so this means now people cannot use a compiler to help get their homework assignment done, because hey, there's no compiler to target the back end using my processor. And two, people cannot post the questions on Reddit and expect somebody else to be able to answer those questions. So that was kind of an interesting side effect. All right, the RAM question. Okay, sure, we can go over the RAM questions from last time. More processor components. There we go. And I'll just go ahead and take the test. We'll go to the preview mode. So I'm glad that Ian is asking the question, because that reflects that Ian did it but didn't quite get something out of it and just wanted to clarify, and that's great. I think the people who copy their answers from somebody else in this lab here are the ones who did not get the benefit of the original purpose of the lab. They might be getting full scores, as opposed to people who might be having some misunderstanding and did not get a full score. But this is minor. Trust me, this is minor. The points for the labs is not that much compared to the exams. It wasn't really designed to be tricky. It was designed so that you have to understand every aspect about a component in order to answer all the questions. So, all right, so let me just kind of go through every single one. Might as well, right? So, W, X, Y, Z all showing triple X, and that has nothing to do with pornography, because X means something is not specified in Logisim. So in order for everything to show not specified, we have to basically not enable the demultiplexer. So B needs to be 0. Okay, so we only want to look into the ones where B equals to 0. So here's one and here's the other one. So the next question is, what are different between these two? So one has disabled output equal to floating, which is an attribute of the demultiplexer, and the other one has disabled output equals to 0. So it would be the former, because we need the output to be floating. Because if the output is a 0, then every single output pin would show basically all zeros. But since in the choice that I have highlighted here that it is floating, so floating basically means you are not specifying anything. Okay, it's not a 1, it's not a 0. It is simply saying I don't tell you what it is. So in that case, it shows as an X. So there we go. We got this one. All right, so W, X, Y, Z are showing 0, 0, 0. That's easy because that's the other one. You still have to turn it off. Okay, you have to basically disable the demultiplexer, but this time you specify that this a disabled output is going to be all zeros, like that. The third one here, W, Y, Z are showing XXX, which means the value is not specified. X showing 0, 0, 1. So now you have to look at X here and ask the question, which output is it? Well, of the 4 outputs, this is output 0, this is output 1, output 2, and output 3. But you want to think in binary because C, which is the selector of which output pin that we want the input to connect to, that's also specified in binary. So X is actually 1 to us in base 10, but in base 2 using 2 digits, it would be 0, 1. So you'll be looking at B being 1 because we want the device to be on. So we're looking at these 4 cases here. We want the we want to have disabled output equal to floating. Okay, okay, this is where I made a mistake. Okay, because there's another attribute that controls whether it's called if I remember correctly, it's called 3-state. Okay, so that is the one that you need to select is output to be 3-state. It's 3-state enabled, and you have to enable 3-state. So other than that, we are looking at b equals to 1, and more importantly in this case, c matters. Okay, because we need to look at c and ask, should it be a 0, 1, or should it be something else? Because c is the selector, and we want c to be 0, 1, so that the input connects to output 0, 1. So let's see here, we got this one and we got this one. Oops, not this one. Oh, okay, so only one of them would work. Only this one is going to work. There we go. All right, and then we got the next one, which is WXZ showing 0, 0, 0, Y showing 0, 0, 1. All right, so that means input has to be 0, 0, 1, but they all have input being 0, 0, 1. I designed that specifically so that people cannot use it as a differentiator of which one is the correct answer. So we want the non-selected output to be all 0, 0, 0, but we want Y specifically to be 0, 0, 1. So let's take a look. Oh, okay, I lied. Okay, there are 2 cases where the input is 1, 0, 1. So we'll be looking at the 4 cases where the input is indeed 0, 0, 1. And we want the device to be on, right? So the device to be on, b equals to 1. And in this case, we want Y, which is 1, 0 in base 2, to get the input. So we want C to be 1, 0. So this is the only one that can make that happen. There we go. And then we have WXZ showing 0, 0, 0, Y showing 1, 0, 1. So that means the input has to be 1, 0, 1 in this case. So now we only have 2 cases here, or 2 items here, where the input is 1, 0, 1. So it'd be between these 2. But only this one, the one that I have highlighted, has the selector being 1, 0, which is basically specifying Y out of WXYZ. So it'll be this one here. And then for this one, we want all the outputs to be XXX, except for W, which shows 1, 0, 1. So once you rule out all the possibilities, however unlikely, this has to be the one that is going to answer that question. So there we go. What does 3-state actually means? Okay, so 3-state means there are 3 possible states for each output. So we already know the 2 that are really that we are familiar with. Okay, it's outputting a 0 or it's outputting a 1. But outputting a 1 versus outputting a 0, it's still having something specified. So the third one, the third state, is to basically say, I'm not going to specify anything. So how can an output pin not specify anything? Simply by not saying anything. Okay, in other words, a device that is outputting a 0 is basically saying 0, 0, 0, 0, 0, 0, 0 all the time. And a device that's outputting a 1 is screaming 1, 1, 1, 1, 1, 1, 1 all the time. And a device that is outputting nothing, the third state, which corresponds to an X, is just not saying anything. Is that okay? In other words, in terms of voting, one is voting yes, one is voting no, and then the other one is abstain, more or less. All right, which is very important, okay? Because there are times when you have multiple devices connected to the same node, and you don't want all of them to be talking at the same time because they can be conflicting. One can be specifying a 1, the other one specifying a 0, and now we have a problem. So it's important to be able, in those cases, to specify, okay, so of the 3 things connected to the same node here, 2 of those things will basically shut up and not say anything, and then the third one can specify a 1 or a 0. So it's important to say that. No, it is not exactly that. Tam, it's high voltage and 0 volt. Okay, so those 2 would correspond to a 1 and a 0. The third one is what we call high Z, or high impedance mode. High impedance mode simply means the output is turned off. Okay, it's not connected to one way or the other way. I can explain that in a little bit more detail, but not today because we are not going to have enough time to answer the question. So I'm going to I will skip to the last one here, and the first one asks, the value of RAM locations becomes 0 regardless of what they start with. So that means you have to use the reset or the clear CLR pin, being a 1, in order to clear everything. So only one of these has clear being a 1. And I have to remember which pin is clear. So clear is this pin here. It connects to input pin E. So E being a 1 is what we need here. So we got this one. There we go. All right. So RAM location 2 has having a value of 5 as the result, as the outcome of what we are doing, regardless of the previous value of location 2 in RAM. So that means we need to specify a write operation to RAM location 2. So to specify a write location, you need the LD pin to be a 0, okay, and you also need the clock pin to go from 0 to 1, and that's after you set up the address pin to specify which location, and also specifying what data should be going into that location using the D pin. But once you understand that the write cycle, which is what this is asking for, requires a rising clock edge, then you can quickly locate and go like, oh, okay, the clock edge is C. So this one has a clock, and it does deal with location 2. So it'll be this one. All right, so this one seems like it's asking the same thing, but it's different, okay? Because this one says, location 0A, okay, 0XA, which is location 1010 because it's a hexadecimal number, gets the value of 1011, which is also in, it's a hexadecimal digit B, but in binary it is 1011. Oh. Okay, so yes, I can address that because but let me just kind of show you what the answer is to this one first, and then we'll get back to the circuit itself. So this one you don't really have a choice but to use this because that's the only option to deal with location A in hexadecimal. None of the other choices would deal with location A. And then we have pin F, specifying the content of location 0A. Okay, I just lied because this is the one that can also that also specifies location A, because location A is basically 1010 in binary. But in this case, we can see how D is a 1, and when D is a 1, it is a read operation. You're not changing the content in RAM. You're just outputting the content of a certain location to the D port of RAM, and so it would be this one here. Alright, so let me address the earlier question here. Yeah, I'm going to extend the deadline, don't worry. Well, let's do that first, okay? So let's do that first, and then I'll get back to the circuit of quote unquote balancing the two pins on the output side or the D port side of RAM. All right, so I'm pretty sure I got 100%. So of the two questions that I answered, so I'm going to take row first. By taking row first, I'm actually doing something that's mean, or someone can conceive as mean. I'll explain that later. Alright, so here's the row taking activity and the answer to. Oh, let me extend the time first. What time is it? It's 44. So I'm going to extend it to 6 p.m. Alright, so there we go. Alright, save. And then the row taking word is TTPASM or uppercase. So there you go. It's sort of, yes. You guys probably know, what I'm referring to, but I'll explain that later. All right, so let me get back to Logisim and actually show you the circuit. Oh, it timed out? Did I forget to change the, did I forget to save it? All right, let me check. Because I'm fairly sure some people got it. All right, so let me just double check. Okay. Yeah, so it is specified as 6 p.m. All right, well, I'm just going to turn on allow multiple attempts. So if it didn't work the first time, just go ahead and redo it. You should be able to reattempt. Oh, okay. That is lame. Okay, so you should be able to do it now because I just turned on multiple attempts. So if you if it timed out on you the first time, you should be able to do it now. All right. Cool, cool. All right, so I am going back to Logisim, and I got all the circuits in a file, so I can just refer to the file here. And the question is, oh, I guess it's not this one, or maybe it is. No, it's not. Okay, so let me see, which one is it? Um, no, that's the same thing. Hmm. Huh. Or maybe it's one of the Logisims. There we go. Okay, that makes sense, right? Test RAM. All right. So the question that Ian was asking has to do with what are these two things doing and why do we have a controlled buffer? And somebody commented that the buffer is one of the most useless devices in the entire Logisim. Well, I mean that's it's electrically speaking, it is a very important device, but from the logic perspective, it doesn't really do much. But this is not just a buffer; this is a controlled buffer, which means it is kind of like a clutch. Okay, it can disconnect whatever is coming in to whatever is going out. So that means depending on what the RAM is doing or what we want RAM to be doing, this control buffer can take whatever pattern is coming from G and feed it through the buffer and feed it into the D port of RAM. So that is useful when you are trying to write to a certain location in RAM because the content has to come from outside. On the other hand, if you want to perform a read operation, then you don't want this input pin to conflict with whatever is coming out of the D port. In other words, D as a port is a bidirectional port in a device because it can both be an output when you are in read mode or can be an input when you're in write mode, when you're writing to RAM. So the traffic control is our controlled buffer here. And the control buffer is controlled in return by this negation gate here, which connects to the LD port. LD needs to be a 1 in order to specify a read operation. So that 1 is going to be negated into a 0, and a 0 to the control buffer means it's asking the control buffer to turn off. Basically, the output here will become basically XXXX in this case because it's all high impedance. So that way, whatever the RAM has to output is going to be okay because there's nothing coming from the input pin G that can possibly conflict with the output from port D of RAM. Yeah, so yep, that's a controlled buffer. Yep, all right. So there we go. All right, so let's move on And I'll first explain why I said what I did earlier by putting the row taking activity earlier can be interpreted as a mean thing, because I have noticed some people just sign off right after I specify the word for row taking. Yep, I actually noticed that because whenever people sign off, there's a tone coming from Discord. Now, when people sign off from YouTube, from live stream, I actually have no idea, okay, because it doesn't send me any notification. But when people sign off from Discord, there's a notification. So, well, I'm guessing those people will be able to do the homework because they already know this stuff, or maybe they'll just really watch the video really quickly before the lab. One way or the other. Okay. Yeah, the value of the live session, is you guys can ask questions. And I can answer the questions right away, or at least respond to the questions right away. And so I think that's the value of the live or synchronous session. All right. Now, it's important to take notes as well, okay? Because it may not be possible for you to kind of jam all of this stuff in your head, during the lecture time. But when you take notes, you are basically, you're writing down what you're getting at that moment. And a lot of the stuff that I'll be talking about today is not captured in a written module. So there's no written module to read about the content that I have here. So, and that makes it even more important for everybody to be present and be taking notes and be asking questions. Okay, if I'm not clear about something, if there's a concept that I just kind of mentioned or tried to explain and it wasn't clear, then ask questions. Okay, so that's important. All right. Okay, so alrighty. All right, so tonight's lab is about the familiarization of the TTP toolchain. But the first thing we need to do is to get the processor up and running. So to do that, and I'm not sure whether you guys want to do this right now or not. My advice is not to, okay? Because if you do this right now, you may not be able to pay attention to what I have to say at the same time. The instruction is already in the lab itself, okay? So that's my recommendation. So what you do is in the lab is you go to the processor subfolder coming from the link that I just clicked on, which is the shared folder at the beginning of the Canvas shell. And then you go to processor, and then once you get to processor, there are 3 files that you need to download. So those 3 files, okay, let me check those specific items. One is regbank.circ, register bank, and I'll explain what it is. And then the last one is processor 0004. So these are the 3 files that you need to download, and I would advise you not to try to do this at the same time when I'm trying to explain it, because I can do this quite fast. And the lab instruction contains instruction to do this already, and everything is being recorded. So I would say try not to do this at the same time, because I think it's much more important to pay attention to the concepts. Because when people are trying to catch up, because I can do this faster, they can basically run out of attention, to focus on what I'm saying. All right, so I'm just going to save it as a specific zip file, and I'll call this p processor.zip. Okay, it's in my temp folder. Where you stash this is entirely up to you, but for the time being, I would suggest you guys to put everything into one single folder. It makes certain things a whole lot easier. I'll explain that also later on. All right, so I am just kind of resizing a window here. So this way, it's you guys can actually see how I do it. Now, if you're in Windows, you obviously do not need to run a command line command in order to unzip the file. But I'm not using Windows, and I'm far more familiar with the command line interface, so I am just doing everything using the command line interface here. So I'm just going to be unzipping the processor.zip file and get the 3 files back here. Alright, so we got a text in your instructions to Logisim on Logisim when you find the folder you said most people put in downloads. Yeah, most people download into the downloads folder because that's the default, and most browsers by default would not ask you where to save your file. It will automatically put everything into the downloads folder. So that's the only reason why I said, okay, you might want to use that as a default folder. But depending on how busy you use or how much you use your browser, your downloads folder may be very cluttered. Okay, so in those cases, you kind of have to find out, how you want to deal with this. It's a browser issue. It's basically how you configure your browser to ask you to where to save a file. So, that's one way to kind of be so that you'll be able to control where the files are saved to. Alright, so once we get here, we can now start Logisim. I got a few Logisim instances started up already, so I'm just going to reuse one of them, like this one. And then we go to File, we go to Open, and then just navigate to the folder, which in my case, is under Temp, and the folder name itself is Processor. So I'm going to put it here. Of the 3 files, the one that you want to open is processor0004.circ. That's the one that you want to open. And so click and then open. And here's the processor. It is busy, okay? It is very busy. It has a lot of components. So I'm hoping everybody actually, try to understand the components, because we see multiplexers, we see a RAM, we see, let's see, we see a demultiplexer here, right? We see tunnels flying all over the place. We see AND gates. We see input pins. That's very definitive of Keanu Reeves, except he didn't quite use that word in John Wick. It's the other people using that word to describe him, right? And here's a ROM, and here's a splitter, here's an adder, and so on and so forth. So I'm really hoping you guys spend some time to really understand how the devices work, because at some point it's going to be very, very important. Alright, so I'm going to go back to a discussion that we had some time ago, which has to do with what is a von Neumann architecture. What makes the von Neumann architecture a novelty at the time? Okay, what is so special about it? So I wanted to see if you guys can remember what makes a von Neumann architecture important, or what makes it significant. Memory is separated. Not quite, but it does have something to do with memory, so that's a very good start. But it's not because it is separated. It has to do with what role memory is going to play in a computer. We got a few people typing. Hopefully you guys are remembering, the significance of the von Neumann architecture. And all modern computers are basically, in one way or another, a von Neumann architecture. You can hardly find anything that is not a von Neumann architecture. Now there are extensions of that architecture called a Harvard architecture, but everything is a von Neumann architecture now. Alright, so let me read. You can read from memory. Nah, that's not why it is called the von Neumann, why it is significant. And Ian is correct. The memory does not need to be physically reconfigured, but reconfigured for what? Okay, yeah, what is the purpose? What is the rationale of reconfiguring the computer or the wiring to begin with? Omer said you can change the values in memory so you can have different programs. Yes, that is an indirect way to describe why the von Neumann architecture is important, and Gabriel nailed it. So Gabriel nailed it because memory stored instructions instead of having to. It's not the punch cards. It's not the punch cards. It's the rewiring of the connections. Okay, so memory is storing the instructions. So that means we have two memory devices here. One is RAM and one is ROM. The RAM is the one that stores the instructions. Okay, so then you might be asking, but then what is the ROM doing, right? So we'll address all of those questions in time. Okay, but right now we'll basically just have to remember the programs that you write turn into memory content, and the memory content is loaded into RAM first. And I got a call. I'm gonna hang up first. So the instruction that you write is going to turn into memory content, and that memory content is loaded into RAM, and then the processor, which is kind of the rest of this entire thing, is going to read location by location from the RAM, and then it will use that content to figure out what to do, what operation to do. Are we going to add? Are we going to subtract? Are we going to compare? And after this, where do we go? Am I going to store something into RAM? Am I going to read something from RAM? And so on and so forth. So this is the overall idea of how this connects all the way back to the discussion of the von Neumann architecture. So there we go. And the next thing we're going to do is to kind of go through the cycle of writing a program. So once again, try not to replicate what I'm doing, because when you're busy replicating what I'm doing, it's harder to pay attention to the concepts, and it's the concept that is important at this point. Alright, so I'm going to start up the assembler. This is called the assembler, and every semester somebody is going to try to download this and open it up in Excel. Do not do that. Okay, this assembler works only when it is opened as a Google spreadsheet. So do not even bother to download it, because once you download it, it doesn't matter what you use to open it, it's not going to be helpful. So just open it in Google Doc as a Google Sheet, and there are instructions for you to make a copy of this. So you're going to have to clone this first into your own Google Drive, and then you'll be able to use it, because otherwise you won't have read access to the assembler. So I double click it, it opens the Google Sheet, and it's really kind of involved. For those of you who are curious, you can kind of go through and kind of see how it is implemented. But the rest of the class, you don't need to do that. All right. So the program always goes to the score, means not score, but source tab. So the source tab, column A, is where the code is supposed to go. Yes, you guys can kind of visit this page as I do things on it. It's not going to be super duper important, right now, but it might be. Okay, but this gives you your own view of the document. So when I switch from one tab to another tab, you guys can stay on whatever tab you want to stay on, which is kind of handy. So I'm not going to talk much about what each instruction is actually doing. So instead of explaining that, I'm just going to put in some active code here, not active but valid code into this program. So once again, don't worry about what each one is trying to do, but these are basically instructions that eventually you'll be writing. And then we'll put a we'll do a CPR BA, and then we'll put a halt instruction here. There we go. Alright, so now I have a kind of really short program that doesn't really do anything that is useful by any means, but nonetheless it is a program. Okay, so when you look at this, you go like, okay, I do not see how this has anything to do with memory, because you remember, the significance of the von Neumann architecture is the instructions are stored in memory, and in return the processor will go to locations, and retrieve the instruction and go like, okay, this, what do you want me to do? Okay, this is what you want me to do, and go to the next instruction location and then read, and you execute the instruction again and then go to the next location and so on. So you look at these four things and go like, but that doesn't seem to specify any content in memory. Well, that's because this is called mnemonics. In other words, now I can just talk about this really briefly, so don't worry if you have no idea what I mean when I say no op, load immediate, copy register, and halt. Okay, because all I want to do is to show you that these are really kind of awkward abbreviations of of operations that we want the processor to do. So they're very, you can say it's cryptic, okay, but it's not nearly as cryptic as their original form. So I'll show you guys what I mean by the original form. So if you go back to the processor's folder, and this time you use Opcode Table. Now, Opcode Table itself is really just a table. It is in the format of a Google spreadsheet, but this is all it is. Okay, it's just for documentation purposes. So this is basically mapping the opcode, which are specified in zeros and ones, to the mnemonics, which are specified in abbreviations that hopefully easier to remember. Okay, so if you look at, okay, I'll just use this as an example. Okay, I'll use these two cells as an example, and let me bump up the magnification first, so this way we can kind of focus on just those two cells. All right, so there we go. So we can see the opcode here, okay, the opcode in bits, binary digits. In this case, it's 01000010, which is 42 in hexadecimal. And the processor is able to interpret 42 in hexadecimal and understand what it is supposed to do. What it's supposed to do is jump if and only if overflow is set. That's what it's supposed to do. So can you remember, okay, can you as a human remember what each 8-bit binary pattern is specifying from the perspective of the processor? The answer is yes, you can, okay, but do you want to? The answer is probably not, because you got other things to do, right? Why do you want to use up a lot of your brain juice to memorize what each binary bit pattern is telling the processor to do? So that's why we have mnemonics. So mnemonics is, yeah, it does build character, but you may not be able to get much else done other than building character. And having a built character by itself doesn't pay, literally doesn't pay. Unless you want to become an entertainer. In that case, it's all about character. All right, but there can only be so many Keanu Reeves. Okay, so we have to understand that there can only be one Keanu Reeves with character. Yes. All right. So getting back to here. So JOI is the abbreviation. It's the abbreviation of jump if and only if overflow, and then the I is immediate. So yes, it is very cryptic, it's very abbreviated, but it still beats. Okay, it still beats having to remember zeros and ones. Now, if you look at column C is a notation. I'm using the C, quote unquote, C notation to represent what the instruction is actually going to do. Now, it's hard to understand this because we don't know what the PC is. Okay, PC is program counter, by the way, but I haven't explained it yet. But we can see the syntax here is very C-like. In other words, I use the ternary expression here. I use asterisk to mean the reference, and then we have your PC plus 1, which is basically just literally whatever PC has plus 1. Okay, and on the in column D, it is a more or less user-friendly description of what it is. So this one means jump if and only if overflow is a 1. So that's how we use the opcode table. Now, in the opcode table, this is an easy one to figure out. So there are ones that are kind of harder to understand, like CPR. Okay, CPR is a great one to look at. So let me go to CPR, and where is it? Okay, I'm just going to cheat and ask, where is CPR? There we go. All right, so CPR is copy register, and basically X specifies one of the four registers and Y specifies the other register. So the operation is to copy the content of register Y to register X. Now the difficulty here is we are not going to need to understand the instructions, but what I'm trying to do here is to kind of show you guys how to why we need mnemonics. Okay, because without the mnemonics, CPR is not a single opcode, it is a family of opcodes. There are 16 opcodes corresponding to CPR. They all start with 0101, which is a 5 in hexadecimal, but then we have the second part of it, or the least significant 4 bits, specified as XXYY. So XX is the 2 bits to specify one of the 4 registers that will take the place of X here. And then YY are the other 2 bits to specify which register will take the spot of register Y here. In other words, X and Y here are placeholders only. They are not exactly a specific register, because X can be one of the 4 registers and Y can be one of the other 4 registers. So if you and the 4 registers are basically named A, B, C, and D. Okay, so register A would correspond to the bit pattern of 00, and so on. And that part is actually explained in this spreadsheet as well, somewhere. There we go. So XX specifies one of the 4 registers. A is 00, B is 01, blah blah blah. YY specifies one of the 4 registers. Same deal. So XX and YY are placeholders, so that I don't have to list 16 different opcodes where they're only different by which register is X and which register is Y. So that's an abstraction right there. Yeah, they're parameters. You can look at those as parameters because they're placeholders, and the actual opcode depends on which of the 4 registers you want to be X, which is the one receiving the value, and which of the 4 registers do you want to be the one providing the value. So Bernard is correct. Okay, that is a very good analogy, so that we use familiar concepts to explain something that is relatively new. Good job. All right, so getting back to CPR, okay, and I lost track of it already. There we go. So if you want to CPR, let's say AB, okay, so you're trying to use register A as XX, and you're trying to specify register B by YY. So we just remember, right? XX should be 00 in this case, because that's what register A is represented as a 2-bit number, and then register B is 01. So in that case, you end up with 5, and 0101 is hexadecimal 5, and then the least significant 4 bits will be 00 for XX, 01 for YY. So together they become 0001, which is just 1 in hexadecimal. So in this case, 51 would specify CPR A, B. So would you much rather remember that 01010001 is copying register B to register A, or would you want to specify CPR, which stands for copy register, and then AB? Well, I mean, that's up to you, but my personal preference is I want to keep the mnemonics. I want to use the mnemonic to specify my instructions. All right. So another kind of trivia here, okay, because we are talking about Keanu Reeves. So as it turns out, the term mnemonic is also related to Keanu Reeves, because he made a movie called gosh, what was the name of that movie? It has to do with mnemonic. Johnny Mnemonic. What's the name of the movie? No, not Constantine. Constantine had nothing to do with mnemonic. Not that he didn't do a good portrayal of Constantine. It was Johnny Mnemonic. That's the name of the movie, Johnny Mnemonic. There you go. Oh, by the way, it's a really kind of cult classic too. I really like that movie. I just watched it like a few weeks ago and rewatched, I should say. It's actually not a bad movie. It's very classic Keanu Reeves, by the way. Yeah. Alrighty. So, exactly. It was great. It was a great movie. Gotta watch that one. All right. So now the assembler's job is to do this. Okay. So this is what the assembler is going to do. The assembler is basically saying, "Give me all the mnemonics." Okay, and I will turn the mnemonics into the binary bit patterns for you. Okay. So that way, all you have to do is to remember the mnemonics, which are I know they are cryptic, but there's a certain pattern to how I name the mnemonics, and they're fairly industry standard as well. So once you understand the mnemonics of one specific processor architecture, moving on to the next one typically is not going to be a huge deal. It's going to be there'll be some time that you need for transitioning, but it's not going to be like super duper difficult. So are we good so far in terms of understanding what is mnemonic and what is opcode? Opcode is what the processor sees, as for the instructions, and the mnemonic is what we prefer to see as the instructions, which is what you're looking at on the screen right now. And then the job of the assembler is to convert from mnemonic representation into the opcode representation, which eventually then will be loaded into RAM, and then the processor can run your program. All right. Yeah, I think it's on Netflix. So far, so good. All right. So the next thing I want to show you is skipping the RAM file first, but go to the Assemble tab. So the Assemble tab is, the way you see it here is already greatly abbreviated because you can see how many columns I have hidden from your view. It went from column A straight to column V, because all of those intermediate ones is where the assembling actually takes place. In other words, I wrote it's not exactly a compiler, but it is it's a program to convert from mnemonic into opcode, and it's all done in Google Sheet. And that's kind of that was a fun thing to do. Okay, I had no specific reason to do it other than I want to see how far I can push a spreadsheet. So it turns out, that's actually doable. Yep. I have no idea. I have no idea whether they know that I'm doing this or not, but it's doable. Anyway, so now we want to take a look at this particular screen because this is a very useful tab from the assembler. On one end, you have column A. Column A is nothing more than just a cleaned up version of what is in your source code. So the comments are all kind of chopped off, and everything is flushed to the left-hand side, and I think all the extra spaces are also removed. So column A is just a replicate of what the source window has. Column V, now this is all kind of self-documented, because if you hover over the header or the first cell of a column, it explains what it is. Okay, so column V is addressed in decimal or in base 10, and then column W is addressed in hexadecimal. So my program is not long enough to show you the differences, but basically if you look at let's say location 10. Okay, so let's say we have a location 10 in column V. In column W, it would have been 0A, because 0A is the hexadecimal or base 16 representation of the same value that we know as 10. Oh, that is funny. I'm just reading the text channel. All right. So what about X and Y? So X is, okay, let me hover over X. So X is the opcode, and if X is the opcode, then what is Y? Y is the immediate value. So, and you can see some instructions like no op only takes up one of the two right? It only has an opcode. It does not have an immediate value. Some instructions like load immediate has two, so it uses 1 byte for the opcode itself, and then it uses another byte for the immediate value. So now the question is, look at column W. Okay, it doesn't seem to make sense, right? And by the way, these are the locations of the opcode. Okay, it's hard for me to point to it because it keeps wanting to pop out the explanation. So this is the location, and this is the content of the location. This is the location. This is the content of the location. This is the location. This is the content of that location. Then you go like, but Tech, don't you have a bug in the assembler? How come it skipped from location 01 to location 01 to location 03? What's happening to location 02? So I'm gonna let you guys think about that a little bit when I'm trying to read the text channel. Oh, this is as far away from Python or Java as possible. Forget the spoon, you need a blender. And Eric is correct. Okay, so Eric is staying on track. Good job. And the 02 location is corresponding to the 17. So that's why that's why on each row we only indicate the start memory location of that instruction. So some instructions are pretty simple. It only uses 1 byte, but some of them, like LDI, will take up 2 bytes. So with LDI, it takes up 2 bytes, which means this is the 6C, which is the content, is going to be stored at location 01. And then the 17 is right next to it. So the 17 is going to be stored at location 02. And that's why the next row starts with location 03. All right. So I want to see if there are any questions. I can see we're having an interesting discussion. But I think this part is important because it's in your lab tonight. Well, not exactly like this, but the concept is. And then when people ask me about that question, I am going to refer them back to, guess what? The lecture. And I might even be kind enough to tell them around 6:20. If I remember 6:20 by the time this lecture ends, I'll be kind and tell those people 6:20. All right. Well, thank you, Mohammed. That would help the entire class until that line of text scrolled off the screen, like in the next 5 minutes. All right, so 02 is not shown on screen because column W is only here to show you the location of the first byte of the instruction. So that's why. Because this is only for documentation purposes. The processor does not need this. I'm showing you this only because then you understand the assembly process. All right, are we good so far in terms of just the general idea of, yep, we start with mnemonics because it's easier for humans to remember, but we want to translate everything to opcode because that's the only thing the processor can understand. But in order to do the translation, doing it by hand defeats the whole purpose of having mnemonics to begin with. That's why we have the assembler doing this job for us. And the assemble tab of the assembler, which is the tool, shows us the memory location, what content or what value is supposed to go where in memory. So once this is all done, then we move on to the RAM file tab. So the RAM file tab looks kind of funky. It's like, whoa, that's kind of the same thing that we saw in column X and column Y, but it doesn't even bother to show us where that stuff is supposed to go. that's because by default everything starts from location 0, so everything is just kind of sequential. So this goes to location 0, 0. This is going to be going to location 0, 1 and location 0, 2. This is going to location 0, 3. This is supposed to go to location 0, 4, right? And this part here is necessary, okay? Because when you try to download this file and then load it into Logisim, it wants to see v2.0 raw as the first line of the file. So this one needs to be here. Now, on the other hand, if your source file has a problem, I'm going to inject a invalid operation here, which is JUMP, because the actual jump instruction is JMP, not JUMP. So you can see how the assembler would actually report an error. So right away, I can see that this is an error. But let's just say that I did not check, okay? And I went to the RAM file right away, and you can see the RAM file is actually giving me a second chance to catch the fact that something went wrong in the assembly process. So so if your file doesn't work, you should probably check the source tab. Okay, one more thing about the source tab that's also important. Now, when I say stuff like that, you probably want to kind of jot down a short note for yourself, so this way you're not going to lose track of that. So the tip is, when you're copying and pasting code from a text file or a source of text, when you're copying and pasting, do not double click, and you see the blinky cursor here, and then paste. Because if you did that, then all of those lines would go to one single cell and the assembler cannot handle it. So when you copy and paste from an outside source, you only want to select, which does not mean double clicking, it's just a single click of a cell and then you can paste. Okay, so this part is really kind of important because there are people who kind of just by habit, double click to specify the content. That won't work. Okay, so you do not want to double click and see the blinky cursor when you paste into a cell, unless you only want to paste one line. Then it works. Alrighty, so now what are we going to do with the RAM file? Okay, so it is also something that you might want to jot down, or at least write down the time, which is 6:27. So what you do now is you go to File, and then you go to Download, and then you specify one of the two last items. Okay, either one would work, but by convention, I just use a .csv, which stands for comma separated value. So I just specify this, and this is also where you might want to really kind of change the behavior of your browser, because you kind of don't want to specify names, like this. Okay. Let me show you what I mean by like this, because I think this part is not visible to you. And there we go. Alright, so by default, it will give it some kind of funky name like assembler-ram file, which is the name of the spreadsheet and the name of the tab or the sheet that we are on. So I typically just kind of rename it to something like test, okay? Test.csv. Remember where you download it, okay? Click, and then you click save. Now the file is saved. And then what do we do? So now the file is no longer on Google's side, it's no longer on Google Drive, it is actually on my local drive. So once it's on my local drive, I switch to Logisim. And where did I stash it at? There we go. So now we go to Logisim, and then what we do is we go to the RAM component. Once you get to the RAM component, right click on it. Okay, once you right click, you will see this menu bar or the menu, and the pop-up menu will have a load image. So this is how you can load a file, which is the file that we saved earlier, test.csv, and load it into the actual content of the RAM component in the processor. So I click load image, and then we specify the folder, which is temp, and then the file name is test.csv, which is really just a regular text file. You can open it with Notepad, and there we go. So you can see 006C1754 are now, and last of all 01 is now specified as the content of RAM. So now the program is ready to run. We have set up everything now in order for the processor to start to read the content of RAM and figure out what it's supposed to do. So are we good so far or not? Just in terms of the concepts, okay? We are not going to be talking about the individual parts of the processor today. Today we just want to kind of look at everything from a we just want to look at the forest, for now, and kind of understand, okay, over here we got this kind of tree, over there we got that kind of tree, and so on. Oh, okay. I'm glad you guys find it interesting. All right. All right. So now what do we do, right? In the assignment, in the lab tonight, you're going to have to run the code. So there are a few ways to run the code. I'm going to demonstrate the first way first. Okay. So the first way to run the program is to run it full speed and just get to the end as quickly as possible. It is okay to do that for this lab. Okay, so don't worry. We'll explain all the kind of fine details of how the processor gets the job done. Just I may not have enough time today to do that. So what you want to do is to go to the simulate menu, and then you go to click frequency, because by default the click frequency is going to be really low, maybe 0.25 hertz, which is once every 4 seconds, which is very, very slow. So what you want to do probably is to go all the way up to 4.1 kilohertz, which is the fastest you can do it. And then after that, you want to turn on simulation. So you want to go to ticks enabled. So let me explain what a tick is first, and then we'll go ahead and do it. So you guys probably remember the clock pin of RAM and the clock pin of a edge sensitive D flip-flop. When you see an upper rising edge, then the device will basically store the content presented at the D port. So instead of having us to click that pin repeatedly, we're just going to wear out your mouse, because it's going to be a lot of clicks. Okay, so instead of doing that, instead of using a regular input pin like this one over here, I am using a clock pin. This is a clock pin. A clock pin is sort of like an input pin, a 1-bit input pin, except that it can automate. In other words, if you go to simulate and you say ticks enabled, the system will automatically transition the zeros into 0 to 1, 1 back to 0, 1, 0 back to 1, 1 back to 0, 0 back to 1, and so on. So it's going to be automatically generate the square wave, so to speak, and then you don't have to do a single thing. You just kind of lean back for a fraction of a second, and then the whole thing is done. Okay? All right, so one more thing before I actually click that button, because the question is, but how do I know the processor is done? How do I know this entire program is done? So there's one pin at the lower right corner here called the Halt pin. I briefly explained, the Halt pin. This is important, okay? Because the name Halt is actually special to Logisim. So when this pin, which is a 1-bit pin, is a 1, then simulation will stop by itself if you run it from the command line interface. Now, we are not running it in the command line interface, which means it's not going to stop, but it will at least tell you that the program is done, and then you can stop the simulation manually. All right, so I see Ian is asking a question. I'll address that one first before I turn on the simulation, turn on the automatic clocking, and then we'll go from there. And there's one more thing I want to show too. Is the value output for clock pins synchronized across all components in the circuit that have the clock pins? That is a very good question, and there's a very quick way to answer that question as well. So remember, when you are using the poke tool, okay, not the pointing tool. So when you're using the poke tool and you poke a wire, it will highlight everywhere that the wire goes to. In other words, this is a tunnel, which means this may not be the only place connected to the clock pin. So when you click on this, it will highlight every single node. It will highlight all parts of the same node. That's the best way to say it. So you can see how clock is going into the register bank. Clock is going into the flags register. It's going into the program counter. It's going into the instruction register. So Ian, you are correct. The clock pin is quote unquote universal. It goes to all of the registers. It goes to the RAM component as well. And it also goes to this microcode pointer register, and it's a very special register, but nonetheless it's using the same clock. So the idea of a clock pin, or the idea of a clock, is kind of like the conductor's motion when you're going to a performance of the orchestra. So when the conductor waves the wind, it's providing a synchronized time base for the entire orchestra. And it's the same thing over here. It is for synchronization purposes. Everybody has to do this now, everybody has to do this now, and so on. So that's kind of telling you why we have edge sensitive devices, because it's for synchronization purposes. Okay, would multiple different clock pins be synchronized, or would you have to trigger them individually? Well, these are all connected to the same node, and which means if logically speaking, they are basically all connected to this single clock pin here. The entire processor has one single clock pin, and it goes to all of the devices. So I'm not sure whether that answers Dylan's question or not. I mean, you can do this manually too. By the way, you can go to you can type control. What is it again? Control T, and it will give you one edge. Every time you type control T on the keyboard, it will give you one edge. All right. So, like if you had two of those and enable ticks, would they both be synchronized? I do not think they're necessarily synchronized, because it depends on the state. So what the simulate is going to do is to alternate the states of those two pins. Now, whether they are both zeros, or one is a 0 and the other one is a 1, depends on what you manually did to the pin before you enable ticks. Alrighty, so I think we got enough discussion to get this whole thing started. So we can either type Control K on the keyboard, or we can just go ahead and use this menu item here to enable ticks. So I'm going to type Control K, because I want to take a look at the Halt pin here and see when it turns into a 1. So here on the keyboard, I'm typing Control K, and it's doing it almost instantaneously, because this program is really small. Now, some of the questions of today's lab is going to ask you, after this operation, what is the value of register blah? Okay, and so to answer that question, you're going to have to look into the component which I call the register bank. So this component here is called the register bank. Instead of double clicking it, because every semester somebody's going to say, oh, to open something, I double click it. Yes, that will work in most of the other types of software, but not in Logisim. So in Logisim, well, actually, I take it back. It does open it up, but not in the way that you want it. So you want to right click on it, and then you select View Reg Bank. And once you get that done, then you actually go into the register bank, and it reflects the state of all the registers at this point. So right now we see register A has a content of 17 in hexadecimal. Register B has a content of 17 in hexadecimal, and that's because we copied. Now, in this specific program, we copied from register A to register B instead of the other way around, which is in the sample code that I showed you earlier when I tried to explain how to use the opcode table. So this is how we can, when you're done with this, you can double click on main to go back to the overall circuit. So this is also one of the things that you have to do in one of the questions in today's lab, is to look into the register bank and find out what is the current value of a specific register. All right, so I'm going to pause a little bit here and see if you guys have any questions about just procedurally what I did. Okay, because obviously I did not spend any time to explain the multiplexers, the demultiplexers, and what they do, and so on and so forth. But I do want to kind of make sure that you guys understand how to specify a program in the assembler, how to take the output from the assembler, which is going to be a specification of what goes into RAM, into the RAM component here. And then once you get there, we know how to run the program. So if you have any questions about just the process of doing this, let me know now so I can kind of talk about that. All right. Will you be explaining the purpose of the register bank in a later class? Yes, potentially even today. It depends on whether we are okay at this point with all the stuff that you need to use in order to get the lab done. How complex will the code be that we need to put into the assembler? Okay, so in prior semesters, we have done recursive subroutines like the Tower of Hanoi, Fibonacci sequence, binary search tree, and so on. So the effect or the outcome of the code that we put into this assembler basically can represent the complexity of certain recursive algorithms, like binary search tree, the stuff that I just mentioned, Fibonacci sequence, Tower of Hanoi. It'll be fun. It'll be fun. I mean, by the end of this semester, you will know exactly how a C program actually runs. Like, where are my local variables? Where are my parameters? Okay, how is a return value processed? And so on and so forth. How is a loop done? How is a conditional statement done? What is a structure? What is a pointer to a structure? How do I access a member of a structure pointed to by a pointer? We'll actually understand all of those concepts by the time we get to the end of this semester. Well, so I hope. Okay, so not a whole lot. Because I had to give my other class a second exam, so that took up a lot of time too. In terms of grading, I'm a huge momentum, so I need a lot of energy to start moving. Once I get started moving, it's not bad. It's just I need a lot of energy to start moving. Alrighty. All right. So any other questions related to the process, okay, how we use the tool? Because if there are no questions about that, I can actually get started with explaining how the processor actually works. How does it get a byte from RAM and figure out what it's supposed to do with it, and then do the next thing and the next thing and the next thing and so on. It doesn't look like we got any questions here. All right. Well, if you guys don't have any questions, I'm gonna move on. I mean, you gotta ask questions when you are not clear how something is done. So I'm gonna make the assumption that we are good there until somebody poses a question. All right. Well, I'm still gonna wait. So if you guys post anything, I'll respond to that. But until such time, I am going to show you how the processor gets things done. So the test instruction is going to be add, okay? Because we all know how to add stuff, so that's going to be a pretty easy one. So the mnemonic is simply add xy, x being one of the four registers, A, B, C, or D, and y is the same thing. So let's just say that I want to add register D to register C. Okay, so according to this column C here, X should be C and then Y should be D. According to the earlier part here, to specify register C, we have to specify bits 1, 0. To specify register D, we have to use bit pattern 1, 1. So that means in order to specify the instruction add CD, where is it again? I kind of lose track of it again. Oh, right here. Okay. Okay. I just did something to the spreadsheet. There we go. All right. So in order to specify the instruction to add register D to register C, the 4 bits here, the 1, 0, 0, 0, that has to be there. Okay. We cannot change that part. The part that we can specify would be the XX and the YY. So I just talked about XX should be 1, 0, and then Y should be 1, 1. So together they become 1, 0, 1, 1. So that means the actual opcode of add CD is going to be an 8 for the first hexadecimal digit, or the leftmost one, and then the next hexadecimal digit is going to be 1011, and that would be a B. Okay, so 8B is what I need to specify in the RAM. So instead of using the assembler for something this simple, I can now go to the processor, and the first thing I'm going to do is to reset simulation. So this way it empties out the entire RAM content, so I can now start a new program. So since I'm not using the assembler, I can just kind of use a poke tool, poke the location that I want to put a content into, and specify the actual content, which in this case is 8B. There we go. And then the next instruction, I want to specify the halt instruction. So this way, when I'm done with the program, it's going to stop, because otherwise it will keep going. Okay, which is not going to be good. So I want to make sure that it does halt. So the halt instruction is pretty easy to specify because it is just 0, 1 in terms of the opcode. So you can see how halt here has an opcode of 0, 1. So I'm going to specify that by hand in the RAM content here. So specify 0, 1. All right. So now we go to the register bank, because we want to know, okay, what's in register C and what's in register D, because otherwise we cannot test whether the program is getting the job done or not. So now we go to view reg bank, and they're both zeros, which is not a whole lot of fun, because if you add 0, 0 to 0, 0, you get 0, 0 back. So there's no way we can actually tell whether the program gets the job done or not. So I would change this to this is the destination. This is where the sum is going to be stored. So I'm going to put a 1, 2 over here, and this is the number being added to register C. So I'll specify, let's say 8 E over here. These are all in hexadecimal. So now we can go back to main and start running the program. So eventually what we want to do, the only component of the processor that can actually perform addition, subtraction, and all of those other things is the ALU, which is the arithmetic logic unit, which is this guy over here. So we want the first input to be coming from register C, and then we want the input 2 to be coming from register D. So basically we want this to go to one of the output of the register bank, such as this one, and then we want this to eventually connect to the other output pin from the register bank, which is this one over here. So to do that, okay, we can see that, oh, how do we get this done? It's basically just a configuration of a bunch of multiplexers and demultiplexers. That's how we get it done. Inside the register bank is another set of demultiplexers and multiplexers. So we have a decoder here, which is basically the same thing as a demultiplexer, where the input is a constant of 1. And then we have 2 multiplexers, each one selecting one of the 4 registers as the output. The other one selects one of the 4 registers as the output. However, keep in mind that these 2 multiplexers have independent selectors. So the first one can be selecting register A, and then the second one can be selecting register D. I'm just using that as an example. Now, can they both be using the same register as the input, as as the register to be passing through to the output? The answer is yes. Okay, you can actually have both of these multiplexers, both specifying the same register to connect to. Let's see, is there a component in the processor that converts hex to binary? And the answer is no, because hexadecimal is more or less just a representation, that's handier. So everything in the processor, everything is happening in base 2. Okay, there's no getting around that one. Now, having said that, if you just want to know what is in register C, you can always just click on this one. Okay, it gets the job done as well. Now, does it show in hexadecimal? That depends on how you configure Logisim. So to make sure that when you poke on a wire, it shows binary and in hexadecimal, this is how you do it. And you might want to jot down some notes, and the current time is 6:50. Okay, because somebody's gonna ask this at some point. So you go to Window, you go to Preferences, and let me drag the window down so you can see it. There we go. And then you go to, which one? Window? Nope. Layout. Yep, Layout. So you go to the Layout tab, and then the first radix when wire poked, that's the one to the left hand side of the slash. And then the second radix is the one to the right hand side. So I have configured Logisim to tell me the binary representation of what's on the wire and the base 16 representation of the same thing. It's just an interpretation thing, right? So there are other options. You can say you can have signed decimal, unsigned decimal, or very rarely, people use octo. I personally do not ever use octo. But obviously in the current assignment in the lab that you're going to do, hexadecimal may be the most useful representation. But before you use the wire value by poking it, before you trust the result here, you better make sure that you configure what base Logisim is using to display the value on a wire. All right, so I hope that sorts of answer Ian's question, because that's not exactly what Ian asked, but I think what he's asking, or the motivation of asking that question, was to see okay, is there a convenient way for us to look at a bit pattern but in hexadecimal representation? So this is one way to do it if it is coming from a wire. All right, so I think that's it. Okay, yeah, I think this is all the instructions that you really need in order to do the lab tonight. So I'm going to stay online, and see if there are any further questions, that I can kind of answer interactively. If not, I'm going to go away, get something to eat, and then come back in about 10 minutes. All right, so Ian is still asking a question, but I don't see any questions from anyone else. All right, so the question is everything happening in the processor using binary? You're only using hex as a personal preference to manipulate? It's not so much to manipulate the simulation, it is just a different representation. In other words, 0001, 0010 as a binary number can be the value it is representing can also be represented as 1, 2 in base 16. So it's more or less just a way of looking at things, but it's not changing the nature of things. It's kind of like people putting on a different shade, right? Some people have tinted sunglasses, right? Some are yellow, some are orange, some are blue, some are green, some are gray. It's really kind of like that. You're basically just changing what it looks like, but it doesn't change the nature of things. Oh, the lab has not been opened. Very good. And that's going to be something that some people are going to ask at some point tonight. It's like, what is the passcode? What is the access code? All right, where is that? Oh, I just got past it. All right, so this is the lab. It does have an access code, but I cannot remember what the access code is. All right, so it does allow multiple attempts, which means some people will be using the infinite monkey approach to do this, but that's okay. Oh, it does not require access code. Okay, so this one has no access code, and I'm gonna enable it. It's gonna do at 9:50 p.m. like so, and save and publish. There we go. The infinite monkey approach, yes. I don't think Shakespeare referred to infinite. Well, it's a quantum computing age, right? Which is in a in a strange way, the manifestation of the infinite monkey approach. Oh, okay. Yep. Yep. Some of you will like. There's a class in a 4-year university as an upper division class. It's called Automata, or the theory of computation. Those are based on Alan Turing's theorized computers. And one of those things is, there are two main types of automata. One is finite state, and the other one is let's see, deterministic versus non-deterministic. Sorry, it's not about finite. It's deterministic versus non-deterministic. In a deterministic finite state machine, it can only be at one state at a time. With a non-deterministic, finite state machine, it can be in any state. So when you combine that with a storage unit like a tape, then you can basically explore many different options at the same time. So there's that. Alrighty. So it looks like we are good to go here. And so I'm gonna close the voice channel and also the screen share. But I'll be back to respond to questions in just a little bit. Give me about 10 minutes or so. Yep.